Werner Karl Heisenberg, the 5th of December 1901 to the 1st of February 1976, was a German theoretical physicist and one of the key pioneers of quantum mechanics. He published his work in 1925 in a breakthrough paper. In the subsequent series of papers with Max Born and Pascual Jordan, during the same year, this matrix formulation of quantum mechanics was substantially elaborated. He is known for the uncertainty principle, which he published in 1927. Heisenberg was awarded the 1932 Nobel Prize in Physics for the creation of quantum mechanics. Heisenberg also made important contributions to the theories of the hydrodynamics of turbulent flows, the atomic nucleus, ferromagnetism, cosmic rays, and subatomic particles. He was a principal scientist in the German nuclear weapons program during World War II. He was also instrumental in planning the first West German nuclear reactor at Karlsruhe, together with a research reactor in Munich, in 1957. Following World War II, he was appointed director of the Kaiser Wilhelm Institute for Physics, which soon thereafter was renamed the Max Planck Institute for Physics. He was director of the institute until it was moved to Munich in 1958. He then became director of the Max Planck Institute for Physics and Astrophysics from 1960 to 1970. Heisenberg was also president of the German Research Council, chairman of the Commission for Atomic Physics, chairman of the Nuclear Physics Working Group, and president of the Alexander von Humboldt Foundation. Werner Karl Heisenberg was born in Würzburg, Germany, to Caspar Ernst August Heisenberg, and his wife, Annie Wecklein. His father was a secondary school teacher of classical languages who became Germany's only Ordentlicher Professor, Ordinarius Professor, of medieval and modern Greek studies in the university system. Heisenberg was raised and lived as a Lutheran Christian. In his late teenage years, Heisenberg read Plato's Timaeus while hiking in the Bavarian Alps. He recounted philosophical conversations with his fellow students and teachers about understanding the atom while receiving his scientific training in Munich, Göttingen, and Copenhagen. Heisenberg later stated that my mind was formed by studying philosophy, Plato, and that sort of thing. And that modern physics has definitely decided in favor of Plato. In fact, the smallest units of matter are not physical objects in the ordinary sense. They are forms, ideas which can be expressed unambiguously only in mathematical language. In 1919, Heisenberg arrived in Munich as a member of the Freikorps to fight the Bavarian Soviet Republic established a year earlier. 5 decades later, he recalled those days as youthful fun, like playing cops and robbers and so on. It was nothing serious at all. From 1920 to 1923, he studied physics and mathematics at the Ludwig Maximilian University of Munich under Arnold Sommerfeld and Wilhelm Wien, and at the Georg August University of Göttingen with Max Born and James Franck, and mathematics with David Hilbert. He received his doctorate in 1923 at Munich under Sommerfeld. At Göttingen, under Born, he completed his habilitation in 1924 with a habilitation script, habilitation thesis, on the anomalous Zeeman effect. In June 1922, Sommerfeld took Heisenberg to Göttingen to attend the Bohr Festival, because Sommerfeld had a sincere interest in his students and knew of Heisenberg's interest in Niels Bohr's theories on atomic physics. At the event, Bohr was a guest lecturer and gave a series of comprehensive lectures on quantum atomic physics, and Heisenberg met Bohr for the first time, which had a lasting effect on him. Heisenberg's doctoral thesis, the topic of which was suggested by Sommerfeld, was on turbulence. The thesis discussed both the stability of laminar flow and the nature of turbulent flow. The problem of stability was investigated by the use of the Orr-Sommerfeld equation, a fourth-order linear differential equation for small disturbances from laminar flow. He briefly returned to this topic after World War II. In his youth, he was a member and scout leader of the Neupfadfinder, a German scout association and part of the German youth movement. In August 1923, Robert Hansel and Heisenberg organized a trip to Finland with a scout group of this association from Munich, Göttingen, Copenhagen, and Leipzig. From 1924 to 1927, Heisenberg was a private docent at Göttingen, meaning he was qualified to teach and examine independently, without having a chair. From the 17th of September 1924 to the 1st of May 1925, under an International Education Board Rockefeller Foundation Fellowship, Heisenberg went to do research with Niels Bohr, director of the Institute of Theoretical Physics at the University of Copenhagen. His seminal paper, Über Quantentheoretische Umdeutung kinematischer und mechanischer Beziehungen, Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations, was published in September 1925. He returned to Göttingen and, with Max Born and Pascual Jordan over a period of about 6 months, developed the matrix mechanics formulation of quantum mechanics. On the 1st of May 1926, Heisenberg began his appointment as a university lecturer and assistant to Bohr in Copenhagen. It was in Copenhagen, in 1927, that Heisenberg developed his uncertainty principle, while working on the mathematical foundations of quantum mechanics. On the 23rd of February, Heisenberg wrote a letter to fellow physicist Wolfgang Pauli, in which he first described his new principle. In his paper on the principle, Heisenberg used the word Ungenauigkeit, imprecision, not uncertainty, to describe it. In 1927, Heisenberg was appointed Ordentlicher Professor, Professor Ordinarius, of Theoretical Physics and head of the Department of Physics at the University of Leipzig. He gave his inaugural lecture there on the 1st of February 1928. In his first paper published from Leipzig, Heisenberg used the Pauli exclusion principle to solve the mystery of ferromagnetism. During Heisenberg's tenure at Leipzig, the high quality of the doctoral students and postgraduate and research associates who studied and worked with him is clear from the acclaim many later earned. At various times they included Erich Bagge, Felix Bloch, Hugo Fano, Siegfried Flug, William Vermillion Houston, Friedrich Hund, Robert S. Mulliken, Rudolf Peierls, George Plotchek, Isidore Isaac Rabi, Fritz Sauter, John C. Slater, Edward Teller, John Hasbrook van Vleck, Victor Frederick Weisskopf, Carl Friedrich von Weizsäcker, Gregor Wenzel, and Clarence Zener. In early 1929, Heisenberg and Pauli submitted the first of two papers laying the foundation for relativistic quantum field theory. Also in 1929, Heisenberg went on a lecture tour of China, Japan, India, and the United States. In the spring of 1929, he was a visiting lecturer at the University of Chicago, where he lectured on quantum mechanics. In 1928, the British mathematical physicist Paul Dirac had derived his relativistic wave equation of quantum mechanics, which implied the existence of positive electrons, later to be named positrons. In 1932, from a cloud chamber photograph of cosmic rays, the American physicist Carl David Anderson identified a track as having been made by a positron. In mid-1933, Heisenberg presented his theory of the positron. His thinking on Dirac's theory and further development of the theory were set forth in two papers. The first, Bemerkungen zur Diracischen Theorie des Positrons, Remarks on Dirac's Theory of the Positron, was published in 1934, and the second, Folgerungen aus der Diracischen Theorie des Positrons, Consequences of Dirac's Theory of the Positron, was published in 1936. In these papers Heisenberg was the first to reinterpret the Dirac equation as a classical field equation for any point particle of spin h2, itself subject to quantization conditions involving anti-commutators. Thus reinterpreting it as a quantum field equation accurately describing electrons, Heisenberg put matter on the same footing as electromagnetism, as being described by relativistic quantum field equations which allowed the possibility of particle creation and destruction. Hermann Weyl had already described this in a 1929 letter to Albert Einstein. Matrix mechanics and the Nobel Prize. Heisenberg's paper establishing quantum mechanics has puzzled physicists and historians. His methods assume that the reader is familiar with Kramer's Heisenberg transition probability calculations. The main new idea, non-commuting matrices, is justified only by a rejection of unobservable quantities. It introduces the non-commutative multiplication of matrices by physical reasoning, based on the correspondence principle, despite the fact that Heisenberg was not then familiar with the mathematical theory of matrices. The path leading to these results has been reconstructed in McKinnon, 1977, and the detailed calculations are worked out in Aitchison et al. In Copenhagen, Heisenberg and Hans Kramers collaborated on a paper on dispersion, or the scattering from atoms of radiation whose wavelength is larger than the atoms. They showed that the successful formula Kramers had developed earlier could not be based on Bohr orbits, because the transition frequencies are based on level spacings which are not constant. The frequencies which occur in the Fourier transform of sharp classical orbits, by contrast, are equally spaced. But these results could be explained by a semi-classical virtual state model. The incoming radiation excites the valence, or outer, electron to a virtual state from which it decays. In a subsequent paper Heisenberg showed that this virtual oscillator model could also explain the polarization of fluorescent radiation. These two successes, and the continuing failure of the Bohr-Sommerfeld model to explain the outstanding problem of the anomalous Zeeman effect, led Heisenberg to use the virtual oscillator model to try to calculate spectral frequencies. The method proved too difficult to immediately apply to realistic problems, so Heisenberg turned to a simpler example, the anharmonic oscillator. The dipole oscillator consists of a simple harmonic oscillator, which is thought of as a charged particle on a spring, perturbed by an external force, like an external charge. The motion of the oscillating charge can be expressed as a Fourier series in the frequency of the oscillator. Heisenberg solved for the quantum behavior by two different methods. First, he treated the system with the virtual oscillator method, calculating the transitions between the levels that would be produced by the external source. He then solved the same problem by treating the anharmonic potential term as a perturbation to the harmonic oscillator and using the perturbation methods that he and Born had developed. Both methods led to the same results for the first and the very complicated second-order correction terms. This suggested that behind the very complicated calculations lay a consistent scheme. So Heisenberg set out to formulate these results without any explicit dependence on the virtual oscillator model. To do this, he replaced the Fourier expansions for the spatial coordinates by matrices which corresponded to the transition coefficients in the virtual oscillator method. He justified this replacement by an appeal to Bohr's correspondence principle and the Pauli doctrine that quantum mechanics must be limited to observables. On the 9th of July, Heisenberg gave Born this paper to review and submit for publication. When Born read the paper, he recognized the formulation as one which could be transcribed and extended to the systematic language of matrices, which he had learned from his study under Jakob Rozans at Breslau University. Born, with the help of his assistant and former student Pascual Jordan, began immediately to make the transcription and extension, and they submitted their results for publication. The paper was received for publication just 60 days after Heisenberg's paper. A follow-on paper was submitted for publication before the end of the year by all three authors. Up until this time, matrices were seldom used by physicists. They were considered to belong to the realm of pure mathematics. Gustave Millet had used them in a paper on electrodynamics in 1912 and Born had used them in his work on the lattice theory of crystals in 1921. While matrices were used in these cases, the algebra of matrices with their multiplication did not enter the picture as they did in the matrix formulation of quantum mechanics. In 1928, Albert Einstein nominated Heisenberg, Born, and Jordan for the Nobel Prize in Physics. The announcement of the Nobel Prize in Physics for 1932 was delayed until November 1933. It was at that time that it was announced Heisenberg had won the prize for 1932 for the creation of quantum mechanics, the application of which has, inter alia, led to the discovery of the allotropic forms of hydrogen.